Bayes theorem is a very powerful tool in probability theory. It helps you adjust your choices based on new evidences or informations. Consider you are a detective and you have to find out who has committed one crime. So initially you may have some hypothesis, but let's say you find out few more evidences. Then your predictions and beliefs has to change, right? Let's see one more example. Consider one doctor has to decide whether a patient has a disease or not, and he or she got few more test results, or the person may be having few more symptoms. So based on this new informations or evidences, the probability of the person having the disease has to change, right? So these are kind of examples where Bayes theorem can be used. So Bayes theorem and conditional probability goes hand in hand, or we can say the Bayes theorem is based on conditional probability. And we'll see in this video how this works. And it is used in various machine learning and artificial intelligence problems throughout various domains, starting from healthcare to sports analysis, stock analysis, weather forecasting, gaming, and whatnot. So we need to learn it.
The Bayes theorem is known after a famous statistician and philosopher, Thomas Bayes. So, this is based on conditional probability. Let's say from the conditional probability for two given event A and B, probability of A given B is probability of A intersection B divided by probability of B, and also probability of B given A is probability of B intersection A divided by probability of A. So we can write as, from this equation we can write as probability of A intersection B will be probability of A given B multiplied by probability of B. Probability of A intersection B is probability of A given B multiplied by probability of B. From this equation we can write probability of B intersection A is probability of B given A multiplied by probability of A. Probability of B intersection A is probability of B given A multiplied by probability of A. But this one and this one is same. Probability of A intersection B is equals to probability of B intersection A, right? So we can write that this one and this one is equal. So probability of A given B multiplied by probability of B is equals to probability of B given A multiplied by probability of A. And then we can derive probability of A given B is probability of B given A multiplied by probability of A divided by probability of B. And this is the Bayes theorem. So let's see why is it useful. I'll just give you a small example. Suppose we have two events. We have one is R, that is whether it will rain today, and C is if it is cloudy today. And if we want to calculate probability of R given C, if today is cloudy, then what's the probability that it will rain today? So that we can calculate from probability of cloudy given rain multiplied by probability of rain divided by probability of cloudy. And why this is useful here? Because for a particular day, suppose we want to calculate uh, if it will rain, given that it is cloudy today. But how do we calculate? Let's say we have one data set for for last month, right? And we are storing cloudy and rain information. And for a few days, like if it was cloudy, then let's say it rained. If it was not cloudy, then also someday it rained, right? It can happen that it was a very clear day, but still suddenly it started raining. So that also possible. There are few other information for the last month or last few months or years we have collected this data, right? Let's say it was cloudy someday but it didn't rain, right? So if we have some kind of data, so it's easy to calculate probability of cloudy given rain, right? So how many days it rained we know, and for those days what is the probability that the day was cloudy. So we can calculate this probability from this kind of data set. This is some evidences we are collecting, right? So that evidences we can use in this formula. Probability of cloudy given given it rained, and probability of rain also we can collect from this data. Probability of cloudy also we can collect from this data set. So if we have some evidences or informations gathered, so from those informations we can calculate this probability, and then from that we can calculate what's the probability that it will rain today given that it is cloudy, right? So this is kind of idea like in what kind of scenarios we can use Bayes theorem. Now we'll see one example. One disease is very rare, say only 0.5% population has the disease. The medical test for that disease is 99% accurate in detecting the disease. Given that the test result is positive, what is the probability of someone is actually having the disease? So let's define few events, right? One event is D, this like someone is having the disease. One event is ND, that is not diseased, right? Positive, this is basically positive result, and negative, that is negative result, right? So what we know from the problem statement, 0.5% population has the disease, so probability of disease is 0.005, because 0.5% population is only having the disease, and so it's very rare disease and the probability is very less. Probability of not having a disease in that case will be 0.995, right? Now let's try to draw a tree diagram. So someone can have the disease or not have the disease. This is a disease path and this is not disease path. So the probability of having a disease is 0.005. Probability of not having a disease is 0.995, right? So if someone is having a disease, there are two paths, right? If someone is having a disease, then also the result can be either positive or negative, right? If someone is not having a disease, then also the result can be positive and negative. So this is basically true positive path, this is false negative path, this is false positive path, this is true negative path, right? So it is said that the test result is 99% accurate. So what are the accurate paths? This is one accurate path because someone is having the disease and the result is positive. This is one accurate path. Someone is not having a disease and the result is negative. This is one accurate path. So and this the result is 99% accurate, right? So this two path probability will be 0.99, right? And this is inaccurate, and these two are inaccurate path. So this is false negative path and this is false positive path, and this two path probability will be 0.01, 0.01. Now what we want to calculate? We want to calculate probability of disease given positive, because we want to calculate what is the probability of someone is actually having a disease given that the test result is positive, right? This we can write as probability of positive given disease multiplied by probability of disease divided by probability of positive. So probability of positive given disease, this is basically talking about this path. Someone is having the disease and what's the probability of positive. So we are talking about this probability, that is 0.99 multiplied by probability of disease. Probability of disease is 0.005 divided by probability of positive, but we don't know yet the probability of positive. So let's see from the tree diagram. We are getting positive result in these two paths. In one path we are having a disease and the result is positive, and in one path we are not having the disease but still the result is positive. So this is true positive path, this is false positive path. So we have to sum them up to get the actual positive probability, right? So we have to sum this path and this path. So that will be 0.99 multiplied by 0.005, that is from this path, then plus 0.01 multiplied by 0.995, that is from this path. So if we just calculate this will come around, I think 0.3322. You can verify this result, but this is the main idea, right? Now, so from the last example we got some idea like how we are calculating the conditional probability using Bayes theorem, but I want to simplify the Bayes theorem little bit more. Let's try to write down the Bayes theorem formula once again. Probability of A given B is probability of B given A multiplied by probability of B. So from the last example we got the idea like how we are calculating the conditional probability using Bayes theorem, but here I want to simplify this theorem a little bit more. Let's try to write the Bayes theorem once again. Probability of A given B is probability of B given A multiplied by probability of A divided by probability of B. But in the last example we saw that we didn't know how to calculate the probability of positive results, right? So we checked for two paths possible for positive and then we summed them up. So I just want to simplify this from this theorem only. So this we can write as probability of B intersection sample space, right? So if this is the sample space, let's say this is the sample space and this is B, right? So B intersection sample space is B basically, right? This part. So we can write this. Also we can write probability of P given A multiplied by probability of A divided by probability of P intersection. This sample space we can write as A union A complement, right? So basically if this is the sample space and this is A, this is A complement, right? So A union A complement is subspace. Again, further simplify. This P intersection this A union A complement we can write as P intersection A union P intersection A complement, right? How is it? So let's say this is B and this is A, right? And they are not intersecting with each other. Then what is B intersection A? B intersection A is in this case empty. But what is B intersection A complement? That is this part. So that is B, right? And also let's see one more scenario where B and A intersect with each other. In that case, B intersection A is what? This part. B intersection A complement, that is what? This part. So if we just do the union of this green and blue part, we'll just get P, right? So this is simple. Now we just try to write it in terms of probability. This one we want to simplify a little bit because we can calculate the probability of B intersection A and B intersection A complement separately. We can write it as probability of B intersection A plus probability of B intersection A complement, right? Again we can simplify as probability of B given A multiplied by probability A of A. This numerator part is not changing, but this one we are just trying to simplify once again. Probability of B intersection A, what we can write it as? Probability of B given A multiplied by probability of A. And how do we write this one? Probability of B given A complement multiplied by probability of A complement. So this is we basically use in many examples, right? So we'll see one more example. A factory produces light bulbs and 95% of them pass the quality control test while 5% are defective. If a randomly selected bulb is defective, there is a 90% chance it will be flagged during inspection. However, if the light bulb is not defective, there is a 10% chance it will still be flagged as defective. That is a false positive basically. So if a randomly selected light bulb is flagged during the inspection, what's the probability that it is actually defective? Let's write down the events. So this and D is now here not defective, and if D is defective, F is flagged, and F is not flagged, right? What's the probability of not defective? Because 95% of them pass the quality control test because they are not defective. So that is 95% or 0.95. And probability of defective in that case will be 0.05. Probability of flagged. Okay, now we can draw a tree diagram again to discuss this flagged and non-flagged part. So if bulb is not defective and defective, not defective probability is 0.95, defective probability is 0.05. And for each defective and non-defective cases, the result can be either flagged or not flagged. Now what it is saying, if we randomly selected light bulb is defective, there is a 90% chance it will be flagged during inspection. So if it is defective, then 90% chance it will be flagged, right? So that is 0.9, right? And then in that case, not flagged, this probability will be 0.1. Also, if the light bulb is not defective, there is a 10% chance it will still be flagged as defective. So if it is not defective, still there is a 10% chance that it will be flagged as defective. So this probability will be 0.1. So this will be 0.9. Okay. So now what we have to calculate is probability of the bulb is defective given that it is flagged, right? That given that the randomly selected bulb is flagged during inspection, what is the probability that it is actually defective? So using Bayes theorem, we can write as probability of flagged during defective, flagged given defective multiplied by probability of defective divided by probability of flagged. But now we see from the previous formula we saw that numerator remains same, but the denominator probability of f, right, like this one and this one, can be written as probability of f given flagged given defective multiplied by probability of defective plus probability of flagged given not defective multiplied by probability of not defective. So this is if you see from this tree diagram also, probability of flag given defective is this path, flag given defective and probability multiplied by probability of defective, and probability of flagged given not defective, probability of flagged given not defective, right, multiplied by probability of not defective. So actually we are just trying to sum up these two parts only, but now we are using this formula. So this comes around 0.9. Probability of flagged given defective is 0.9 multiplied by probability of defective. Probability of defective is 0.05 divided by probability of flagged given defective is 0.9 multiplied by 0.05 plus probability of flat given not defective, right? Probability of flat given not defective, this one, that is 0.1 multiplied by 0.95. So this is 0.1 multiplied by 0.95, right? So if we just calculate this will come around 0.045 divided by 0.14, which will be approximately 0.3214. We can verify the result, but this is how we calculate the conditional probability using Bayes theorem.